So this talk is all about finding and exploiting novel flaws in Java applications. And I say novel in the sense that they're at least somewhat particular to Java applications. There's nothing in here that's really super cool. There's no crazy technique that anybody's heard about before. Actually, there is, but that's at the end, and I couldn't get RCE using it. But I'm just going to go through some sort of basic things that allow you to effectively get RCE in Java applications that a lot of people don't know about, and then build on that into some sort of new research of ways that we might be able to get RCE, but I haven't been able to figure out how to yet. So just a little bit of background on me. I have, I guess like a lot of people, no formal background in security. My education is actually in climatology. If you ever fly a plane in the southern hemisphere, the weather messages that get transmitted to the plane where the pilot comes on and tells you what the weather is going to be when you take off and when you land, I wrote the system that, that generates and transmits those messages. It's in pure PL SQL, running on an Oracle database. Horrid. So for the last 5 years, I've mostly been focusing on security. I worked for Red Hat. I was the manager of a large part of Red Hat's security team for several years. Now I work for a startup called IIX, the International Internet Exchange. And we're working a lot of software-defined networking technologies, so I founded and lead the Open Daylight and ONOS security teams. Here's all the things that we're going to go through. I won't read through them one by one, but the point is I only wanted to focus on stuff that's relatively interesting and new. I'm not going to bore this audience by going through Web App Sec 101 with cross-site scripting and SQL injection. That would be insulting. So hopefully it's all a little bit more interesting. This guy over here, for people who don't know, is Lord Tuskington. He's a very famous walrus, and he's presented at KiwiCon in the past, and I really wanted to get him some more global cachet, so he's going to be participating a little bit in the presentation today. Actually, the last time that I sort of used Lord Tuskington in public was at the end of RuxCon in 2014. And they had the lightning talks at the end, and I'd participated in the chili eating competition, which came just before the lightning talks. And that put me in like some sort of psychedelic realm where I didn't know what was a good idea and what was a bad idea. And in the end, I wound up dropping some 0-day on CyanogenMod. And people in the media came up to me afterwards and said, we want comment on this 0-day that you just dropped. At the time, I worked for Red Hat, which was a vendor. I couldn't go on record saying this guy from Red Hat Product Security dropped 0-day on CyanogenMod. So Lord Tuskington took the rap. And here it is. You can read the write-up of that issue on his blog. He really enjoys trolling Google and Cyanogen, so he's my alter ego. So let's start. Let's use that as a segue to start by talking about these SSL issues. And this was one of the articles that was written after RuxCon 2014. And you know, as is claimed there, over 10 million Android users running CyanogenMod and its derivatives are vulnerable to man-in-the-middle attacks. Through a lack of hostname verification in the SSL library that was being used. CyanogenMod categorically denied it in public. In private, I emailed them and they admitted to it and said they didn't want to admit it in public because it would make them look bad. So how did this come about? Working in Red Hat Product Security was really, really interesting because across, it would be the same in any major vendor. I'm sure Oracle or IBM is the same. We've got like a dozen different major products that are built on Java, and all Java applications use an insane array of libraries. It's completely nuts. If you look at any of the major, in quotes, enterprise Java software, you'll have like 100, 200 third-party components in there easily. So I would be triaging and looking at reports of security vulnerabilities in all of these components. If a component was in any one of those products, I was looking at reports of vulnerabilities against it. So I sort of noticed a pattern that there was all these flaws in major components like Commons HTTP Client, Apache Access, and several others, where there was a lack, either a complete lack of hostname verification in the SSL implementation, or the hostname verification that was implemented was flawed. And this is an example of the flawed code. I hope that's large enough that people can see it, by the way, but I'll distribute the slides later anyway if you can't read it. But the interesting part is the line that says if toc.substring, etc., equals ignore case cn equals. So basically what they're doing is saying everything that comes after cn equals, that's the common name that we're extracting. So you can just, as shown at the bottom there, you can just sort of inject O equals foo, cn equals apache.org, and it will accept apache.org as the common name in that certificate. So what that means is you could create a certificate signing request with O equals that down in the bottom. The actual CN that's in the CSR would be your legitimate domain. Then you go to any one of the SSL providers that add such huge value to security of the ecosystem by verifying that your domain name is legitimate and nothing else. They completely ignore the dodgy O value. If in the CSR you've put that CN equals string before the O string, the one that comes last will be matched, and then any of these clients will match your certificate as belonging to that domain name that you've injected. So very easy man-in-the-middle attack. Exploitation relies on tricking a CA into signing such a cert, and for a while people thought, oh, you know, they'd probably catch it. But it turns out no. Some engineers from Facebook who found one of the instances of this issue proved categorically that you could get many, many CAs to easily sign these requests. The really funny part is, if you go back, they've done all this sort of manual string tokenizing and parsing stuff. The patch was to use the inbuilt function that comes with the Java libraries for handling X509 certificates. So here you go. If you have a look at the Cyanogen mod issue, it's a slight variation on that vulnerable code that I showed you earlier, but you can see it's basically got exactly the same kind of problem in it. Now the interesting part is this variation of the vulnerable code turns out that it comes from a code sample that's shipped with the Oracle JDK 1.5 docs, which is, what, 8, 9 years ago? I don't know, it's old. It's very old. And so I tried to find the root of it, and as far as I can tell, that was the root of this code sample. And it's been copy-pasted in so many different places that if you go onto GitHub now and search for this snippet, you'll find it. So that's how I had the Cyanogen mod 0-day, was as part of triaging this issue across all of the components that Red Hat shipped, I went and just wrote a script that searched for this in GitHub, and one of the instances I found was the Cyanogen mod instance, but there's many, many more in there. So that's the first category of issue that I wanted to talk about, the SSL issues. And I think it kind of sets the scene for what I'm doing here, that none of these issues are super elite. This is just a string parsing vulnerability, but it gives you potentially SSL man in the middle against umpteen million phones. So in the same vein, authentication bypasses. And there's a few variations of this that are common in Java applications. The first one is just straight up logic errors in the security constraints. I'll give you a demo of one of those in a second. More interestingly is HTTP verb tampering. Are people familiar with HTTP verb tampering? Anybody? Going once? No? Okay. So what can happen is, in Java applications especially, but I presume this also applies to various other frameworks, when you set security constraints on a web resource, like a URL path, you can specify that that constraint only applies to particular HTTP verbs. So what people would do is say, oh, okay, well, I'm going to be parsing gets and posts and maybe puts, so I will put the security constraint on the URL that applies to gets and posts and puts, and that will be applied. But a lot of people would forget about the head method. Again, you can find many examples of this out there today if you just look on GitHub. And the head method is particularly useful for HTTP verb tampering. So the idea is somebody set up a security constraint against a URL that blocks all these other verbs but not head. Now, JBoss Web and Tomcat, JBoss Web is actually a fork of Tomcat, are the two main servlet processors used in the Java world. They're the two main open source code bases that will actually be processing the requests and applying the security constraints. And what they do is, whenever there's a head request, they actually run the code for processing a get request. They run the do-get method. And the reason they do that is that a head request is meant to return what you would get from a get request, but without the body. It needs to include things like content type, content length. If you've got a dynamically generated response, how do you know the content length unless you actually go through the processing at the back end? So if you can use a get request to actually perform some malicious action, then you can make a head request without authentication. And we'll get to an example of that in a second that was widely exploited. The first one is just an example of lack of sane authentication constraints. So I was doing an audit of Fabricate and Horde.io, which are Apache Carafe-based middleware products that they're under the Apache umbrella. And I noticed that they have this port.io Carafe terminal that lets you run commands. Not operating system commands, but Carafe commands, administration commands for the environment. And I thought, oh, look, it's got a cross-site request forgery flaw. And I wrote up a little reproducer there and made it work. But then I realized, hang on a minute, I don't even need to be logged in for my CSRF reproducer to work. It's not actually applying authentication to this path at all. Because down here, as you can see in authentication filter.java, they were only authenticating paths that start with those certain prefixes, and the path to the Carafe terminal didn't match the prefix. So there you go, you have remote unauthenticated command execution. Just like the curl command there, you just pass in, so there you've got OSGI shutdown -f, which is just shut down the container, force it, don't prompt me, and that will run. I can do a live demo of that, but I'm actually looking like I'm gonna run a little bit over time, so I might skip that one and come back to demos at the end if I have time. But it's as easy as it looks. I'm not gonna show you anything exciting by demoing that. And the patch, again, is just ridiculous. It's trivial. All you do is you say, oh wait, we want to authenticate all paths, not just these paths that we already thought about. Going back to the issue of HTTP verb tampering though, this was an issue in 2010, and this was the first time that I was working for the Red Hat security team that I got woken up in the middle of the night to deal with an emergency. It was actually the only time that I got woken up in the middle of the night. And what happened was there was a worm going around that was actively exploiting all of the vulnerable JBoss servers that it could find, and it was a worm, so that as soon as it got in there, what it did was set up a command and control bot that was speaking to an IRC network, and then it would just randomly scan blocks of IP address space and infect other systems. And within a day or so, every vulnerable system on the internet had been compromised. If today, I've set up several honeypots, if you put a unpatched JBoss system on the internet, you'll get compromised within a day. Absolutely guaranteed. And the issue was that there's these administration interfaces to JBoss, and the security constraint to those administration interfaces had this HTTP verb tampering flaw in it. It said that the security constraint applies to GET requests, it applies to POST requests, but not to head requests. The administration interface allows you to manipulate Java beans, mbeans, which are server-side components that expose various functionality. That doesn't necessarily get you RCE, but it turns out that the mbeans that are deployed by default on vulnerable JBoss servers include one called the BSH deployer, or the bean shell deployer, which allows you to deploy code to the server by executing methods on the mbean. And if you can deploy code to the server, you can just deploy a command shell with no authentication, and you can run arbitrary commands. So that's how it was exploited. There's Metasploit modules and everything for this now, so it's trivial. The really interesting part of this was that the actual issue, the HTTP verb tampering issue, was fixed several years before the worm came out. So the number of Red Hat customers that got compromised was practically zero. I only ever heard of a couple of cases. But the issue was that for the purposes of making it easy for the developer, the upstream release applied no authentication by default on any of the admin interfaces. As is very common with a lot of projects today, they say, oh, well, in production, you have to change the password. In the supported product, it had authentication applied by default, and people had to choose a new password. There was no default in there. So most of the systems that got compromised were actually the upstream releases that had no authentication anyway. So, you know, the HTTP verb tampering attack would work if there was a vulnerable system with authentication, but of course it will also work if there's no authentication at all. So that was just an interesting lesson. So the lesson is always include default authentication authorization. And ever since then, whenever I've been dealing with developers and they've resisted, I tell them this story and they go, oh, yeah, okay, all right. We'll apply it by default. This is where I'm going to diss Argod. He's not here, is he? Or anybody knows him? He's an asshat. And I'll tell you why. Did we learn our lesson from this? And I would say, no, not really. I found a separate kind of instance of the vulnerability, which was that there are other administration interfaces, the HA servlets, or high availability servlets. It's just the high availability version of the thing that was originally exploited that was also vulnerable. Turns out it couldn't actually easily be exploited because there was a second layer of authorization being applied. But anyway, it was potentially exploitable. What I since found was that Argod and others took a lot of these flaws that I and others have found, including these ones, and then just found all the instances where commercial vendors are embedding the vulnerable components in their commercial products and then reporting the flaws to them via things like zero-day initiative and getting money for them. So I think he's reported variants of this flaw about 3 or 4 times. It's the exact same flaw, it's just that the commercial product is embedding a vulnerable version of JBoss AS, and rather than saying, oh, it's a vulnerable version of JBoss AS, saying, oh, it's a flaw that's unique to HP ProCurve Manager or some other commercial product that's built on top of JBoss. So I thought that was really interesting, and I wanted to name and shame, but I also wanted to say if you have no morals and you want to make easy money, take all the instances on my slides today, find other instances of them in commercial products, and report them to ZDI. It obviously works. The other form of authentication bypass that's quite common in Java applications, but also in others, is the unauthenticated authentication mode of Ldap. Is anybody familiar with this at all? Okay, cool. So it has this fantastic feature where there's various ways that you can apply authentication to an Ldap server. One of them is called unauthenticated authentication. So what it means is you supply a username, but no password, and it will automatically be authenticated. Now the intention of this is that it's used to bind to the Ldap server, then you would actually query the Ldap directory and check your credentials. But it's very, very common that people just say, oh, well, binding to the Ldap server constitutes authenticating. They don't realize that the Ldap server has unauthenticated authentication enabled by default, which most of them do. And as you can see in the RFC, they've even called this out at the bottom, saying operational experience shows that clients can and frequently do misuse this. So it's kind of a design flaw in the RFC, but also a flaw in the way that people are implementing it. So there's just some examples in the Java world. If you look up Ldap unauthenticated authentication, there's many examples for all kinds of applications, languages, and frameworks. Okay. You have to tell me what's so funny. So the next thing I wanted to talk about was Xxe. This again is probably not new or interesting, but it is particularly interesting in the context of Java applications for one reason, and that is that most, if not all, Java APIs for processing XML do not disable entity expansion by default. And the reason they don't and won't do that is because several of the JSRs, several of the specifications that they have to implement require it to be enabled by default. So I've contacted the maintainers of various XML processing libraries written in Java, asking them to disable external entity processing by default as Microsoft.NET did in, I think, 2003, and they say we can't because we'd break compatibility with these specifications. So all you've got to do to fix it is follow the OWASP guidelines, which helpfully tell you what to do, except that, as you can see there, up until June 2014, they didn't. They were missing any guidance on parameter entities. So in order to disable both general and parameter entities, you have to set 2 different configuration parameters. The OWASP guidelines were telling people just to disable general parameter entities, and so pretty much all Java applications were at that point in time vulnerable to parameter entity Xxe attacks, which it's been shown can get you complete exfiltration of arbitrary data on the server. People are now starting to fix it, but it's still extremely common. So here's just an example of one that I found by grepping the code in REST-Easy, which is a REST API framework. Exploiting it is very easy. You just do the standard kind of 2-step parameter entity Xxe data exfiltration attack, and you can get anything that you want from the server. Again, the patch is trivial. It's just adding that one line, set feature, external parameter entities false. If you want to find a lot of these, Xxe flaws are so easy to find in the Java world, so easy. And there's a really, really good tool for it if you don't have the source code. If you have the source code, just grep, really easy. If you don't, there's Xxe Bug Find, which basically does the same thing, but it works on compiled Java bytecode. So it compiles that to an AST, and then walks through the tree, matches patterns, and it's actually, the really cool thing about it is that the pattern matching is decoupled from the way that it analyzes the bytecode. So you can write your own rules. Some of the rules in it are actually flawed. It gets you false positives and false negatives, but because the engine is really well written, you can just write your own rules and fix it up. as an example of finding flaws with Xxe Bug Find, here's one at the bottom in the Play framework that I found. Never used Play, don't know how it works, never read the code, never written a line of code for it, and managed to get credit for finding a flaw that took 2 seconds with Xxe Bug Find. So that's Xxe. Okay, the next one I wanted to talk about is command parameter injection. So this is interesting. Obviously, OS command injection is a huge problem. Don't need to tell you guys about that and how it works. But typically speaking, Java applications are not easily vulnerable to this. Unless you can control the complete input of what goes into the command string. Say it's running ls or cp, and then you can control one of the parameters to that. You can't just put semicolon or double ampersand in there and run another command later. That doesn't work. Because of the way that getRuntime.exec is implemented in Java, it tokenizes the command string and splits it out and says the first thing before a space is the command, and everything else is a parameter of that command. So you can't easily just inject commands like that. But so that's good, but it also means that developers are a little bit lazy about it because they say, you can't just inject commands, it's not such a big deal. They forget about sanitizing input. But if you can control parameters, you can still do a lot of things. So here's a great example of that with Openssl. Openssl is like a Swiss Army knife. Most people know that you can use it to sign certificates and create keys and so on, but it can act as a HTTP client. You can do anything with Openssl. It's practically a mini operating system. So if you can control arbitrary parameter input to Openssl, I consider that effectively equivalent to RCE. Here's one that, so this is 0 day by the way, that I reported to them in September 2014. They still haven't fixed. Their response was, can you please write a patch? To which I said, no, can you? Here's some suggestions. It's still not fixed. It's in Apache Ambari. Apache Ambari is a system for provisioning and managing large deployments of big data tools like Hadoop and Apache Spark. And so it has this REST API that sets up certificates for managing and deploying all of that infrastructure, but you can inject arbitrary parameters into the Openssl command that it runs. Okay. Next one on my list is Xsl Extensions. Has anybody heard of this one? Any show of hands? No? Okay. So, interestingly, I don't think this is common in many other languages. I haven't seen it. But in Java, most of the Xsl processing libraries allow you to embed code inline in a style sheet, like Java code or JavaScript code, inline in a style sheet, and have it executed when the style sheet is applied to transform an XML document, which is really useful. If you want to call out to a third-party system to get some data, you want to do some complex processing, yeah, Picard right there, then it's really useful. But obviously, it basically just gives you the ability to run arbitrary code if you can control the Xsl style sheet that's used. So that's a little bit more tricky, because being able to pass an XML document to a server-side process or an application that will be passed through an Xsl transform is pretty straightforward. Being able to control the Xsl style sheet is more difficult. Also, you can disable, these extensions are enabled by default. They can be disabled manually in code, but then a workaround was found, which is mentioned there. So if people are using an unpatched version of Xalan, which is the predominant Xsl parsing library in Java applications, then even if they did explicitly disable the extensions, you can work around it. I can talk about that flaw in much more detail if anybody is interested. It basically involves embedding a style sheet in a style sheet, and then the embedded style sheet having the code in it and the checks not working with nested style sheets. It's a very interesting flaw though, really cool one. So there's an example of embedding some code in there. Whenever I do remote code execution examples, rather than popping a calc, I pop events. The guy who taught me how to do Java security, Mark Schoenefeld, that was always the way that he would demonstrate RCE, is by popping events, which is an open source PDF viewer. So out of respect for him, I always do that. So the question becomes, how can an attacker supply Xsl that's going to be used on the server side? Well, the first example that I found of this was in Apache Camel. So Apache Camel is a, how would you put it? It's kind of like a routing and translation engine for messages. It allows you to, it's for implementing kind of enterprise integration patterns. So you take data from one system in one format, run it through a Camel transformation process, and then push it out in another format. So it can take XML over HTTP, turn it into a serialized Java object, and push it out over RMI to an IIOP server, or whatever you want. Anything to anything kind of mapping. So one of the transforms that it allows you to do is XSL style sheets. If the input message is an XML document, you can pass it through a style sheet and then output it. And I originally reported this to them, and I was like, oh, it seems theoretically like a flaw, but unless you can control the style sheet on the server side, it's not really exploitable. Maybe it's impact low. And one of the developers said, oh, wait, there's this HTTP header that you can provide, Camel XSLT file name, where you can say, for my message, please use the following style sheet. And by default, any Camel route or any Camel endpoint will accept XML documents. So all you need is the ability to write a document or a message to a Camel endpoint, and you have RCE. So I'll give you a demo of that one. So this will walk you through what's going to happen. I've got this test.xsl, which is my attack. Right? You can see it's just the one that I demonstrated earlier that's going to pop events. So what I do is I copy it into a TMP directory, and then I create TMP input and TMP output. Camel is designed to be able to read and write messages from any kind of transport mechanism. One of the things you can use is just a local file system directory. So I use that because it's easiest. So then I've got a little bit of code that's going to run, which is a Camel server process that I'll show you in a second. That's just monitoring what's in TMP input, running it through the style sheet, and then pushing the transform document into TMP output. So there it is there. And the main point is that from line in the middle. So that's a Camel DSL that allows you to write those kind of expressions. And I guess that's pretty self-explanatory. So pray to the demo gods. Yes, there it is. So there you go, that's events. So there's various other examples of this kind of flaw. There's a whole list of them there. Really interesting one is in Apache Solar, and we're going to come back to that later. Apache Solar is a document search engine, and yeah, really interesting flaw there, but we'll get to that in just a minute. In order to make that one work, the thing I need to talk about next is path traversal. So once again, kind of trivial category of flaw that I imagine everybody knows about. Two things that make this interesting in the Java world. One is, up until about a year and a half ago, there was no poison null byte checking in Java's handling of file paths. And you think, well, wait, it's a managed language. It has managed memory. Why would a poison null byte attack work? Well, it's because, in the end, it's making calls down to native libraries. The native libraries that it was using to handle file paths, of course, would interpret a null byte as terminating a string, and there was nothing in the JDK or the JRE that was stripping that out. So that's one. The other is that people often don't realize that people are using Java on Windows or that they're using it on Linux. A lot of developers are either Java on Linux developers or Java on Windows developers, and they don't really take the other case into account. So there's an example. Can anybody tell me why this vulnerability only applies to Windows? Anybody yell it out? Yeah, it's checking for a // not a \\. And this is really, really common because the developers are running Linux, they're using Linux for their production infrastructure, they just don't even consider the fact that people are running it on Windows, which they are. A lot of people are running Java applications on Windows. So that's an example in Undertow, which is a servlet processor. Here's another example that you could call this path traversal, but it's even sillier than that. There's no path traversal. A component called Uberfire, which is part of a large rules management engine that's quite widely used, contains these file upload and download servlets. And they don't apply proper authentication or authorization. There's absolutely no path checking in there at all. So you can just upload a file with an arbitrary path, download a file with an arbitrary path. If you can upload a file with an arbitrary path, then easy. You can just upload a command shell, a command JSP shell, and you've got RCE. How do you get RCE? By downloading an arbitrary file? Well, on most Java application servers, the authentication credentials are stored in files on disk that are readable by the process that's running the application server. Very few of the production instances that I've run into actually factor authentication out to Ldap or something else. And none of the Java application servers have good support for one-way cryptographic hashes in passwords. They're all using something like the mechanism specified there in order to encrypt their passwords. So, cracking that is quite straightforward. If you can read the password file from an application server, then you can just crack the admin credentials, get into the admin interface, and then upload arbitrary files, and you've got RCE. So that's also one of the reasons why those Xxe flaws are such a big deal. You get a parameter entity Xxe flaw in some random Java component, all of a sudden you can use it to exfiltrate the admin credentials for that server, and you've got RCE. So those were all kind of roundabout ways to get code execution. Let's talk a little bit more about just like going straight for it. A lot of Java applications or Java components use expression languages. There's a variety of expression languages that are out there. There's one just called EL, or expression language, which is a formal specification. There's also another one called MVEL, there's SPEL, the Spring expression language. And this is what allows a lot of the magic in Java web frameworks to actually work, these expression languages. Generally speaking, if an attacker can supply expression language, then they can execute arbitrary code. There's been a lot of kind of interesting flaws recently like this, like the Elasticsearch ones, where you could supply Groovy, which is kind of similar to an expression language, and then you could use reflection from the objects that were available to you to get other classes, get runtime, exec arbitrary commands. So similar kind of attacks apply to most Java expression languages. How do you supply arbitrary expression language that's going to be executed on the server? There's a variety of ways. Here's an example of one that I found. So I have to give credit here to a guy from New Zealand called Adrian Hayes, who originally figured out the issue. I just found instances of where it was exploitable. Seam is a web development framework for Java. It was quite popular in the sort of mid to late 2000s. It's a little bit less popular now. It's on the way out, but a lot of applications are still using it in production. And Seam has a cool feature that allows you, when you're writing log messages out on the server side, you can put expression language in the calls to write the logs. So what you can do is sort of say, it's almost kind of like a format string vulnerability, that you say what you're logging is an expression, and then what you're meant to have after it are arguments that fill in the values in the expression. But people who don't understand it will just say, okay, I'm going to log this string, and then string concatenate in a user-supplied parameter, which will get joined onto that string, not realizing that the entire string is going to be executed as expression language. So all you have to do is find an instance where the person is not calling the logging function properly, as in this example here. They're string concatenating in the client and server values, and these are client and server version values. The client value is specified as a HTTP parameter, so all you have to be able to do is make a request to Zenata saying, I am using version string of EL, and that will get executed on the server side. As I said, Elasticsearch has had a bunch of issues around this. It was using MVEL in search queries by default. They attempted to fix this by sandboxing it, which totally didn't work. just recently, and yeah, they wound up abandoning it, saying, you know what, the idea that we can have this cool feature in our search engine that allows people to just execute arbitrary expression language as part of a query is completely unworkable from a security perspective, and they just took it out. Now I'm just going to check my time. No, I'm not going to have time to demo that one, sorry. But there's an example exploit. This is kind of a more difficult than necessary one, because rather than just executing a command, what we're doing is reading files and then outputting the contents of those files. But it's just expression language. Another example of that is, as I said, the Spring expression language. So a textbook example of this kind of flaw would be where you have a tag in a JSP page that's saying evaluate this Spring expression. If that came from, say, parameter.pwn, param being HTTP get or post parameter, then again, an attacker could just insert expression language in and exploit it. That's not a flaw in Spring. That's a flaw in any application that's using the Spring eval component incorrectly. So am I correct in saying you just called out 1 minute at the back there? Okay, give me 2 maybe. So I'll end on this point of binary deserialization, which is where things start to get really interesting. Binary deserialization in Java is a native mechanism, and when you are serializing and deserializing objects, there are some helper methods that a class can implement called readObject and readResolve. And so they're meant to say, okay, when you're serializing or deserializing this class, some magic has to happen, and you can just put code in those methods. If there was ever a flaw in that code, and you were able to send a serialized instance of an object to a server, and it would deserialize it, then you can trigger that code. It's in the readObject method. That's quite easy to do because a lot of, for example, REST frameworks allow you to use binary Java serialization as a transport mechanism, and there are various examples of that flaw. Where is there a flaw in readObject or readResolve? Here's the best example, and this is really cool. So this is for a component called disk_file_item, which is an Apache Commons upload, but it's also embedded in Apache Tomcat. So about 50% of Java applications have this class on their class path. And what it will do is, because disk_file_item represents a file on disk, when you try to send it a serialized instance of that and it's deserializing it, it wants to create an instance of that file on disk. And the way that it creates it is, as you can see there, new file tempdir temp file name. Temp file name is controlled by the attacker. That's part of the serialized object. If you were using a version of the JDK that didn't have patching for a poison null byte attack in there, then you could add a poison null byte to the end of temp file name, and now you can specify the absolute path. So you can upload an arbitrary file to an arbitrary path. So now you've got a command shell and you've got RCE. I can go on from there with various further research, but that's all I have time for. So I'll wrap it up there and see if anybody has any questions.
Do any of these issues affect Android apps or OS?
They could. I mean, it's all just Java. So any of these categories of flaw could affect Android. None of the ones that I've outlined today specifically do, but they all could. Android apps would be vulnerable to all these issues.
Thanks.